Day 1, Problem 1. Part A. Rewrite the number into standard form. And the first thing I'm going to do is copy down that number. Thinking ahead, noticing that the exponent is positive 7, that's going to cause me to move that decimal point 7 spots to the right. And so I've left some space here to accommodate moving to the right and filling in some placeholder zeros. Again, the reason for moving to the right 7 spots is that an exponent of 7 on the 10 really means that I'm going to multiply by 10, multiply by 10 a second time, multiply by 10 a third time, multiply by 10 a fourth time, and so on. And each time a number is multiplied by 10, it becomes larger by one place value. For instance, 2.5 multiplied by a single 10 becomes the number 25. 25 multiplied by a 10 would become the number 250. The number continues to become larger and larger each time you multiply by 10. On this problem, we need to multiply by 10 7 times, and so that requires moving the dot 7 spots to the right. 1 spot to get past the 5, and then 6 more spots to put the decimal point here with several placeholder zeros filled in. So this will become 2, 5, and then 6 zeros. 1, 2, 3, 4, 5, 6. The decimal point is at the end. We can come back from the right 3 spots and put in commas, 3 more spots and put in a comma, just to help identify that number as 25 million. Now part B. This time the number is 1,020, and the decimal point is at the end. We want to convert this standard number of 1,020 into scientific notation. Now in scientific notation, instead of having several numbers to the left of the decimal point, we want to write it so that there's only one digit to the left of the decimal point. That means we want to put the decimal point here so that this digit is the only number to the left of the decimal point. That's going to require the dot to be moved 1, 2, 3 spots. And so our answer is 1.02 and then times 10 to the third power. Now day 1, problem 2. Solve the equation, and here is the equation, and part B, check our solution. So in part A, let's copy that equation down. All right, there it is. And here's the equal symbol separating the left side from the right side. And solving the equation means to isolate its variable on one side of the equal sign and put any known numbers to the right of the equal sign. So let's put the variable x on the left side of the equation. We need to remove this x term. So underneath, subtract 0.2x, and to keep the equation in balance, subtract 0.2x on the left side. 4.2x subtract 0.2x is 4x. The plus 1.5 can be brought straight down, equals 0.2x subtract 0.2x is 0, and the 9.5 can be brought straight down. Now here's the x term, and next to the x term is plus 1.5. Let's remove that. Subtract 1.5, subtract 1.5. The 4x comes straight down. 1.5 subtract 1.5 is 0. And on the right side of the equation, 9.5 subtract 1.5 is 8. One more step to go and we'll have the x alone. We have 4x, or 4 times x, is equal to 8. And by dividing by 4, we can get these 4's to cancel, isolating the letter x, and over here 8 divided by 4 is 2. So x equals 2 is the value that we believe is correct for x, and in part B we can check that that really works. So we're going to take the original equation, substitute our solution in place of the x to see if it works. Right, there's what the equation looks like with the number 2 filled in for the letter x. We want to know if the expression on the left side of the equation is equal to the expression on the right side of the equation. 4.2 times 2 is 8.4. Over on this side of the equation, 0.2 times 2 is 0.4. 8.4 plus 1.5 is 9.9. Does that equal what's over here? 0.4 plus 9.5 is 9.9. Because these are equal, our solution checks. X is equal to 2 is the correct solution to use for the variable x to make the left side of this equation truly equal to the right side of the equation.